All right, so the problems that we're going to work with here are a little bit different than what we're used to. So far, okay, problems we've had so far, right? We've had ones like y equals 3x squared minus 7x plus 4, okay? And what did we do here? We took d dx of both sides, right? So we had dy dx equal to, you know, whatever this is, so 6x minus 7, right? So if you could see here, the problem y equals blah, 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 the y value, the y variable is distinctly separate from the rest of the equation. So it's one where you could separate out the y, right? And then you could just take a derivative of both sides like that. But now, how about if you had a problem like this? X squared plus y squared equals 9. You can isolate y, and then we'll see some problems where you cannot isolate y. But if you look at the graph of this, it's that circle. X squared plus y squared equals r squared, right? It's a circle with radius 3, okay? So when we find dy dx, right? When we find dy dx, what is it that we're doing? It's how does y change with a change in x. Is that right? Yeah. So if I go to the positive, if I go over on the positive x-axis, right, and I take a look at different values of x, and if I'm looking at the different slopes, so look at the slope there, and look at the slope here, okay? But now take a look. If I go over the same amount here, right, the slope is different. So the change in the slope, it doesn't just depend on the y, it depends on the x and the y, all right? So now, if you look at this, the graph has a well-defined slope at nearly every point. But the process by which we're going to find dy dx here is called implicit differentiation. And the reason is y is not explicitly separate. And you'll see some more examples where that's more the case. So what we do is this. We treat y as a differentiable function, and we differentiate both sides of the equation with respect to x. Okay? So basically still we need to find dy dx. So here's what we're going to do. We have x squared plus y squared equals 9, right? What we're going to do is this. You know how when we take x squared here, when we take the derivative, we get 2x plus, right? But now, what are we looking for at the end of the day? We need dy dx. Okay? So what we're going to do is we're going to take d dx of this entire thing. So now, d dx of x squared is 2x. d dx of this is 2y dy. That's how we treat it. Okay, so you take a derivative, it becomes 2y. So what we're going to be doing here is we're going to be taking a derivative of the x and the y independently of each other. So here it'll be 2y, but then we need to tack on dy dx is equal to 0. Okay, so this is how we do implicit differentiation. In implicit differentiation, right, you take, okay, so you have x squared. Before we had x squared plus 3x equals y, right? So what did we do? We took d dx of this and d dx of that, right? dy dx. So what did we end up with? dy dx was, 2x plus 3. That's because all that equal to y. Now you have a y squared, not just a y. So how am I going to get dy dx? Right? I need to take a derivative of this first, and then I have dy dx. Y as a differentiable function, and we take a derivative with dy dx. Now we have to solve for dy dx. Okay? So let's solve this for dy dx. 2y dy dx is equal to negative 2x, right? And then we can get rid of the 2's. So then what? Divide by y, divide by y. So dy dx is equal to negative x comma y over y. So what does this tell you? What does this tell you? This tells you, okay, so in the ones that we were doing before here, our slope, right? Here the slope is 6x minus 7. It only depends on the x value. But now my slope is negative x over y. So it depends on the x and the y. So for example, if I go over here to like x equals 1, let's say, what's the derivative at x equals 1? What's the slope? Well, if you go here, that's how the slope of the tangent line looks. But at the same point, x equals 1, there is another point in the graph with a completely different slope. Okay? So it's not enough to say what is the derivative when x equals 1, because you've got two different slopes. Your slope depends on the value of x and the value of y. Okay? That's why it's implicit differentiation. Slope depends on both. All right, so let's take a look at this one. Find dy dx if y squared is equal to x, then find the slope at these 2 points. Okay, what does y squared equals x even look like? That's a parabola, but it's sideways, right? So it looks like this, right? That's how it looks. So now we have y squared is equal to x. And now if I want to find the derivative of this is implicit. I bring down the 2, so it'll be 2y dy dx is equal to 1. So divide by 2y, divide by 2y, dy dx is 1 over 2y.
Can you see 1/2?
This is the most efficient way. As long as, mathematically you're correct, you could say whichever you want. Okay, so that's dy dx. So now it says evaluated at the point 4 comma 2 and 4 comma negative 2. So here is notation. Dy dx at the point 4 comma 2 is, and so now here you have x and here you have y, right? So this is going to be 1 over 2 times, this one only calls for the y, so it's that, so it's negative 1 over 4. Oh wait, there is a negative. Oh, no, there isn't, sorry. 1 over 4. It's 1 over 4. Yeah, the other one. So then the other one, dy dx at 4 comma negative 2, that one is 1 over 2 times negative 2, negative 1 over 4. Okay? So this is one where you have to do it by implicit differentiation. Because if I ask you, hey, find the slope of this when x is equal to 4. You're like, okay, x is equal to 4. 1, 2, 3, 4. Okay, so do you want the slope there or do you want the slope there? All right, you have two locations at x equals 4 where I could, where you could find the slope. So that's why it's implicit, okay? Because the slope at x equals 4 also depends on where you are on the y values. Okay, let's do another one here. Find the slope of the circle at the point 3 comma negative 4. Okay, so we're going to find it using implicit differentiation. So 2x plus 2y dy dx equals how much?
0.
0, good. Okay, so now 2y dy dx is negative 2x. Dy dx is how much? Negative x over y. So here's one where the slope depends on x and y. So now, at the point 3 comma negative 4, what's the slope? Negative 3 over negative 4, just 3 over 4. Yeah? 3 over 4 is the slope at the point 3 comma negative 4. Question?
Yeah, why is it negative 3?
Because it's negative x over y. Okay, one more. Show that the slope dy dx is defined at every point on the graph, blah, blah, blah. Okay, so that's just too much information for me, right? So I got to divide and conquer. Show that the slope, okay, dy dx. I need dy dx. Let me just do that first, and then I'll go back and see what it is that it was asking me for. Okay, so dy dx of this. All right, so let me just copy that over here. So 2y is x squared plus sine y. All right, I'm going to take a derivative of 2y. It'll be 2 times what? Dy dx equals 2x plus cosine y dy dx, right? So with the y's, you're going to be doing chain rule, okay? With the y's, we're doing chain rule. So we had sine of y. Outside function is sine. I take a derivative, it's cosine. And then I take a derivative of the y, dy dx. Okay? Now you have to combine the dy dx's. So let's bring this term over to the left. So 2 dy dx minus cosine y dy dx equals 2x. That's unconventional, by the way, to write the dy. It'll be dy dx cosine y. It kind of hurts my eyes, but I'm just going to do it. Okay, because right now, can I factor out a dy dx?
Yes,
Yes, you can. So dy dx, 2 minus cosine y, is equal to 2x. And then what am I going to do? Divide by the parenthesis. So dy dx, which is what I want, is 2x over 2 minus cosine y. Okay, good. I found the derivative. Great. That's not what the question was asking me for. What was the question asking me for? Show that this is defined at every point. What does it mean to be defined at every point? It's basically, what's the domain? All reals, right? Yeah. So domain is negative infinity to positive infinity. Okay, is the domain here all real? Domain is the x values. Are there any values of x for which this doesn't work? No, there are no values, so the domain is all reals. I asked you, yeah. So for dy dx, we got this. Domain is the x values, right? Are there any x values for which this will be undefined or not real? No. Okay? So domain is all reals here.
That's all you have to say?
Yeah. Okay. implicit differentiation process. So here's what we're going to do, right? We're going to differentiate both sides. So this is just a summary. This is what we've been doing with respect to x. Collect the terms with dy dx on one side. Factor out dy dx. Solve for dy dx. The ones we've been doing now are like the boring types, okay? Really, the more exciting ones are ones like the one we're going to do right now. Okay, find the tangent and the normal to the ellipse, blah, 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 at the point here. Okay, tangent, okay, we got to find slope, right? And then it's all downhill after that. Okay, let's find the slope. Okay, what is it that we have to find the slope of? X squared minus xy plus y squared equals 7. X squared, totally cool. XY, we got issues there. Why? Here, I have x times y. I have to use the product rule. I know. No. Yay. Okay. So, x squared will be 2x minus. Now, for the xy, I have to do product rule. So, u is x, v is y. What's u prime? What's v prime? dy dx. Yeah, an implicit differentiation. Okay, so now remember this minus here. Make sure your bookkeeping is in order here because you don't want to lose track of that negative, right? So now in parentheses, it's going to be x dy dx plus y. Okay? Plus, now I'm continuing back to my y squared. What'll be the derivative here? All right. Equals. Thank you. Okay, so now the calculus part is pretty much over for now. Okay? The rest is more algebra-ish. So 2x minus x dy dx minus y plus 2y dy dx equals 0. Well, not yet. I was just distributing now. Now, though, we're going to leave the dy dx terms here and bring everything over to the other side. So, x dy dx plus 2y dy dx is equal to negative 2x plus y. Yes, sir. Oh, it's negative x. See? Keep track of your negatives. Okay. Here?
Yeah.
Well, it was the product rule. Okay. Now, we're going to factor out a dy dx. And here, this gives me negative x plus 2y equals negative 2x plus y. So dy dx, negative 2x plus y, negative x over negative x plus 2y. Yes and no. Okay, so normally we switch the terms around so that the negative is inside. So basically, we just rearrange and, well, we write it like this. Yeah, y minus 2x, 2y minus x. Okay? Math people hate having dangling negatives. It just looks cleaner. Okay, so that's dy dx. Okay, fine. Still not what I've been asked for. What is it that I want? The slope of the tangent line. So the slope is dy dx evaluated at the point negative 1, 2. So for all the y's, I put in a 2. For all the x's, I put in a negative 1. So y plus 2, not y. 2, well, let me take more steps. 2 minus 2 times negative 1 over 2 times 2 minus minus 1. Four over 5. Yay! Okay, so the slope is 4 over 5 for tangent. So the equation of the tangent line is y minus 2 equals 4 over 5 x plus 1. And how about the normal line? Reciprocal, negative reciprocal, x plus 1. Fabulous. Isn't that cool? Okay, so higher order derivatives. Remember? So what if you need like the second derivative, the third derivative, and we have to do it using implicit differentiation. So let's do it. Use implicit differentiation to find dy dx and then d squared y dx squared. Okay. We don't panic, we just do one at a time. So let's go with dy dx. Okay. 2y dy dx plus what? 2, good, equals 2. That's it. Now, can we get rid of all those 2's? Yeah. So now I can factor out a dy dx. So I have what? Y plus 1 equals 1, because I divided out a 2. So dy dx, oh, I love this one, is equal to 1 over y plus 1. Simple enough. We're done with that one. Okay, now, okay, so now we have, let's just write it over. Here's what we have. We have dy dx. What we're going to do is we're going to take ddx of this. Okay. Well, we will. Okay, here, ddx of y is d squared y over dx squared. That's the derivative twice. Equals. We're going to take the derivative of 1 over y plus 1. Let's do quotient rule. So, low, what's d high? 0. Love that. Take high, d low is what? dy dx. Right? Over y plus 1 squared. Yeah. So now d squared y over dx squared is equal to. Okay, so that goes away. So we have negative dy dx. Well, because there is a minus here, right? Because it was take high d low. Over y plus 1 squared. Okay. We can't have dy dx show up in a derivative. That's silly. What is dy dx? 1 over y plus 1. Yes. 1 over y plus 1. Yes, goes in there. So, d squared y dx squared is equal to negative 1 over y plus 1 over y plus 1 squared. Do you cancel it out though? Let's see. This is negative 1 over y plus 1 divided by 1 plus 1 squared is times 1 over y plus 1 squared. We don't cancel it out. Yes, cubed.
Would you rather have us write that?
Oh, you are going to write it that way. Okay?
Wait,
So, okay, so it's this divided by that. meaning this times 1 over that, right? A fraction divided by something is the fraction times the reciprocal. Now I have, in the numerator, 1 times 1, 1, well, negative 1. In the denominator, y plus 1 times y plus 1 squared, y plus 1 cubed. So finally, that is d squared y dx squared.
Why is it dx3?
Huh?
You know what I mean? Why is it?
Oh, I don't know. Oh, why is that one 3 you were saying? Oh, sorry, I just got in the... Okay. Okay. All right, so we've done derivatives, and we've done derivatives including powers, right, where you bring down the exponent and then you subtract 1. And we've been doing this with the square roots, but let's do it a little bit more formally. So let's see what the power rule looks like for rational powers of x, meaning x to the power of a fraction. 7 over 2, 3 over 2, and so on, 2 over 3, okay? So it works in the same exact, it works in the same exact way. It works in the same exact way. N comes down, the exponent comes down, and then you subtract 1. So let's do 1. Okay. Here's a little note. If n is less than 1, then the derivative does not exist at x equals 0. And we'll see why. Okay. So let's take a look at this first one. We have 4x to the power of negative a half, right? What we're going to do is we're going to take, Right, but you'll see why. The negative half will come down. So dy dx is going to be negative a half times 4, x to the power of negative 1/2 negative 1, which is negative 3 over 2. So dy dx is negative 2x to the power of negative 3 over 2. But you know we don't like those negative exponents. Dy dx is equal to negative 2 over x to the power of 3 over 2. And you can see that when x equals 0, the derivative doesn't exist. Okay? Yeah. The square root of x to the third would be okay. Yeah. So this would be the same as negative 2 over root x cubed, like that. It's the same. Okay, what's going on with this one? B. Huh? Product rule. And then eventually chain rule within that. Okay, so u is equal to x, v, x cubed plus 1 to the half, exactly. So u prime is 1. Now v prime is 1/2 x cubed plus 1 to the power of negative half times what?
Wait, why is it not? Oh.
Times 3x squared. So v prime is 3x squared over 2, right? X cubed plus 1 to the negative half.
Wait.
I combined the 3x squared with the half.
Oh.
Okay, so this is why it's important to write down all the steps, right? Because if you can't do it mentally. Okay, so let's see what y prime will look like.
So you don't distribute the half to
No.
the...
Y prime is going to be u v prime. So x times 3x squared over 2, x cubed plus 1 to the negative half, plus x cubed plus 1 to the positive half. Okay? So u v prime plus u prime v. Now, I have an x cubed plus 1 to an exponent, x cubed plus 1 to an exponent. I need to factor out the one with the lower exponent. Which one is the lower exponent? Negative 1/2. So y prime is going to be, I'm going to factor out. Okay, remember, factoring out is the same as dividing the term. Yeah. So this will cancel out. So I have left, what? 3x cubed over 2. That's 3x cubed. Squared times x is 3x cubed. Here, the same base, different exponents that you have to subtract. Half minus negative half will be 1. So it'll just be x cubed plus 1. Okay? Not even close. We got to do common denominator, right? So can I multiply this by 2 and divide like 2 over 2 to make it common denominator? Yeah. So now y prime, right, is going to be, so this is 1 over x cubed plus 1 to the half, right? And here I have 3x cubed plus 2x cubed plus 2 all over 2.
Does that come from doing, like, where does that come from?
I distributed the 2.
Okay.
So now, okay, so here I had 3x cubed, and then here 2 times this. I distributed, so it's 2x cubed plus 2, right? Now here inside, I'm going to multiply these two fractions, all right? Combine these two fractions. What do I have in the numerator? 1 times this. Well, what is this?
3x cubed.
5x cubed plus 2 over 2x cubed plus 1 to the half. Yes. Okay, so let's do, we have to do both. Shh. All right. This one's actually simpler, so let's do this one. We're going to bring the 1 over 3 over, right? So y prime is going to be 3 times negative 1 over 3, 2x to the negative 1/2 plus 1. And now here you have to subtract the 1. So negative 1 over 3 minus 1 is negative 4 over 3. Times the derivative of the inside. So the negative half will come down. So it's 2 times negative half x to the negative 3 over 2. Am I writing too small? Here. Is that better? A little bit. Okay, so let's clean this up a little bit. This is negative 1. Okay. And then we have 2x to the negative half plus 1 to the negative 4 over 3 times negative x to the negative 3 over 2. Okay. Negative, those are going to neutralize one another. So I can't factor anything out either. So y prime, I have this to the power of a negative exponent. I have this to the power of a negative exponent. They're all going to go downstairs. So it's 1 over 2x to the negative half, which is really 2 over root x plus 1, times x to the power of
Like, if we write
3 over 2.
1 over 2, it's not going to be points off. Like if we write it,